Hi, my name is NURIN Muhammad Noor. This is my research for final year project entitled Epileptic Seizure Prediction using EEG data, supervised by Associate Professor Dr. Nur Hashimah Ahmed Hassan Malim. But before I proceed, I want you to close your eyes. Imagine you are having a good time strolling at a park, but suddenly someone catches your eyes. You notice she's having jerky moves. Her eyes blankly stares to the sky, and she is unconscious. Oh my goodness, she's having a seizure. Even worse, she is not prepared with medicine because she also did not know that seizure will attack her that day. This is actually a problem to epileptic seizure patients, as seizure can happen at any time. What can we do to solve this? Would you believe me if I say, with machine learning, seizure can be predicted before it attacks? So, if they are alerted that there is an incoming seizure, they will get prepared at least with medicine. Yeah, that's where my final year project research comes in, entitled Epileptic Seizure Prediction using EEG dataset. Well, actually, there are a lot of attempts to predict seizure using EEG, but the nature of EEG is that the data dimension is very huge that can affect the performance of the classification of ictal, which is seizure, and pre-ictal, which is before seizure. That's why my research focuses on finding time before seizure onset and compare the performance of the classifiers, which is support vector machine, against different dimensionality reduction methods. So, these are the outputs that I should get by building three models with classification, accuracy, and time prediction as the matrices. Well, first model only involved a classifier, namely support vector machine or SVM. Second model uses the help of principal component analysis or PCA onto SVM. And third model uses Stochastic Neighbour Embedding onto SVM. So, how would this dimensionality reduction boosted the classification of ictal and pre-ictal using SVM? Which model would you think would perform the best? Before revealing you to the results, let's see briefly how this research has been conducted. First, using CHB-MIT dataset, I extracted 47 seconds of pre-ictal, which is period before seizure, and 90 seconds of ictal state, which is during seizure. Then, I removed the noise and applied discrete wavelet transform to decompose the noise into its significant frequencies. Well, my EEG dataset has 256 Hz of sampling rate, but I only select the frequencies that are approximately 2 to 32 Hz because they are the frequencies that are significant to seizure. For each of the decomposed signal, I extracted 7 features, which are maximum values, variance, interquartile relation, skewness, standard deviation, kurtosis, and mean absolute values. After that, for a clearer view, I built 3 models. The first model is that the NOOR dimensionality reduction applied. Second model, using PCA, and lastly, using t-sne. Model 1 uses all the 28 original components. With PCA algorithm, we managed to reduce the dimension from 28 components to 6 components. Using t-sne, the algorithm managed to reduce from 28 components to 2 components. All of these 3 models then were classified using the best classifiers for epileptic seizure cases reported by previous researchers, which is support vector machine. To predict time, we applied firing power algorithm. Now, it's time for me to reveal the results of my research. First, let us look at model 1, where we get 54.11% of classification accuracy. Basically, if the SVM classified the data as 1, it should be, say, as ictal of seizure. However, if the SVM classified our data as -1, it should be pre-ictal or before seizure. And according to firing power algorithm, if the pre-ictal states is consistently quantified 7 times, which is the threshold, as pre-ictal, then they are guaranteed as pre-ictal, where alarm should be generated to alert the patients that there is an incoming seizure. But however, for model 1, it is not satisfying the threshold, and therefore the time prediction is 0. Now, let's move on to Model 2, where we get 94.95% of classification accuracy. So, this model managed to satisfy the firing power algorithm threshold. Therefore, we managed to get 2 times of pre-ictal state, which means during the first pre-ictal state, this patient has 4.4 minutes to get prepared before the seizure attacks, and during her second seizure attacks, she has 80 seconds to get prepared. Now, for the last model, we managed to get 63.64% of classification accuracy, and there is one time where this model managed to satisfy the threshold. Therefore, we get the time prediction, which is 28 seconds. This means, using this model, this patient can has 28 seconds to get prepared before the seizure attacks. Now, for important findings, we managed to get the addition of PCA to SVM had boosted SVM classification, whereby with SVM alone, the accuracy is only 54.11%. But when PCA is added to SVM, we managed to get 94.95%. So, this has proved that PCA is able to choose only meaningful data to be fed into SVM. And the addition of t-sne to SVM had also boosted SVM classification, but not as good as PCA, but still better than SVM alone. Our research had contributed to 2 main aspects. The first one is applying firing power algorithm to different dimensionality reduction. Previously, firing power was found applied to Yang 2018 with no dimensionality reduction. So, we widened the firing power application by using it to compare against different dimensionality reduction methods. Second, relationship between time and accuracy. So, our work had proved that accuracy played an important role in getting the best prediction time before seizure onset. So, based on what I presented earlier, do you agree that with machine learning, we can know when seizure is about to attack its patient? If yes, that girl earlier would have an ample time to get prepared, at least with medicines before the seizure attacks her. Problem solved, case closed. With that, thank you.